Hello, I am Susan Osterhaus, the Outreach Specialist for Mathematics at the Texas School for the Blind and Visually Impaired. Today, the title of my presentation is A Comparison of Nemeth Code and UEB Math. My sponsor is the Pearson Assessment Center. If you are a Braille reader, there is a Braille file located at http://accessibility.pearson.com/braille4math-science. Prior to proceeding with this presentation, we highly recommend embossing the Braille examples that will be shown during this presentation. There are side-by-side comparisons and spatial arrangements that are not adequately displayed on a single-line refreshable Braille device. The agenda for today is as follows: definitions, brief history of Braille math, the learning of mathematics, input from those in the STEM fields, published research, math and science samples of UEB and Nemeth, including a number line graph, code books and guidelines, and references. I will begin with some definitions. BANA, Braille Authority of North America. Their mission is to assure literacy for tactile readers through standardization of Braille and/or tactile graphics. Established in 1976, this group includes national consumer organizations, Braille producers, the Library of Congress, transcribing organizations, and others. ICEB, International Council on English Braille. Their purpose is to coordinate and improve standards for Braille usage for all English-speaking users of Braille. Here are more definitions. EBAE, English Braille American Edition, our current Braille code, a set of rules that govern the transcription of literary Braille. UEB, Unified English Braille, a unified code developed by ICEB, adopted by BANA on November 2, 2012, to replace our currently used literary and computer Braille code in January 2016, uses upper cell numbers. Nemeth Code, our current Braille code for mathematics and science notation, developed by Dr. Abraham Nemeth, which BANA voted to maintain on November 2, 2012. It uses lower cell numbers. Even more definitions. STEM, an acronym referring to the academic disciplines of science, technology, engineering, and mathematics. The term is typically used when addressing education policy and curriculum choices in schools to improve competitiveness in science and technology development. TVI, Teacher of the Visually Impaired. ABL, Alliance for Braille Literacy. More information can be found at www.all4braille.com. NFB, National Federation of the Blind. More information can be found at https://nfb.org. And now for the way it was. Before the 1960s, blind children were usually educated in residential schools for the blind. All their teachers knew how to read Braille, could create Braille materials, and read the students' materials. Transcribers could only produce Braille by hand, either using a Perkins Braille writer or a slate and stylus. Multiple copies could be produced only by using a thermoform machine. Then we saw a beginning of change. Much changed in the 1970s. Public Law 94-142 provided that blind children should be educated in the, quote, least restrictive environment, unquote. This law accelerated the trend toward blind children being educated in the public schools. This led to an increased need for Braille transcribers. The Braille code for mathematics changed several times during the first half of the 20th century, but by 1972, the Nemeth Code for Science and Mathematics Notation was the standard. So, what's in place today at BANA? Their website is located at www.brailleauthority.org. Nemeth Code for Science and Mathematics Notation, 1972. Braille Code for Chemical Notation, 1997. Music Braille Code, 1997. Computer Braille Code, that's CBC, 2000. EBAE, English Braille American Edition, 2002. Guidelines and Standards for Tactile Graphics, 2010. Braille Formats, Principles of Print to Braille Transcription, 2011. So where are we going? Now, with various combinations of internet media, speech output, Braille displays, scanning, and OCR, Braille translation software, and Braille embossers, blind people can read in a matter of moments virtually anything created by anyone, with the exception of the STEM fields. However, expanding audio access to mathematics expressions by students with visual impairments via MathML is coming. Nevertheless, Braille under the fingertips is still a requirement for the majority of blind individuals working in the STEM fields. And now for some comments from a teacher who has lived some of this history. This includes comparing Nemeth and UEB from the perspective of a math specialist who is also a teacher of the visually impaired. That's TVI. And that would be me. So here I go. In 1978, I came to the Texas School for the Blind. Yes, it was called TSB in those days. I was certified to teach secondary mathematics, but with no knowledge of how to teach blind students and no knowledge of literary Braille or of the Nemeth Code. My predecessor was long gone, and none of the teachers at TSB could teach me the Nemeth Code, including the Braille teacher at that time. They had always used the Taylor Code, which they said did not support higher mathematics. I started teaching myself the Nemeth Code, and I absolutely fell in love with it. It was very logical and even included valuable symbols that were not available in print. Remember, even print was linear in those days. For example, in Nemeth, when writing superscripts, there is a going up symbol as well as a coming back down symbol. When you had to type on a typewriter or use ASCII, you did have the caret or the going up symbol, but there was no equivalent for coming back down. When writing fractions linearly in print, it was horrible. You never knew when one fraction began and another ended. The Nemeth Code had an open and close fraction indicator. Ah, true love. I had always been taught to speak math correctly so that anyone could write perfect math notes from just listening. Speaking from a Nemeth Code perspective made this so easy for my students. As soon as I would say, quote, open fraction, unquote, they were often brailing the most difficult fraction. When I first came to TSB, the highest level of secondary mathematics being taught was the equivalent of a 2-year pre-algebra class. Thank goodness I was ignorant to the belief at the time that the average blind individual could not do higher mathematics. I just knew that I had to learn how to teach these students. I had always believed in teaching with a multisensory approach and using tools with universal design. And lo and behold, this worked with my blind students. Once I learned the Nemeth Code, it was the glue that held the math together. I was soon teaching a variety of high school math classes for students on both the more vocational track and the academic or college-bound track. Math requirements have continued to grow more rigorous, and we expect that trend to persist. At present, in Texas, graduation requirements for the recommended high school program are 4 credits in both upper-level math and science. In 2011, a female Braille student at the school scored a 5 on the AP Calculus exam. By the way, that's the highest possible score. We are now seeing the first generation of adult Braille users that were educated by TVIs who only learned Nemeth code, as opposed to the Taylor code. These young adults learned Nemeth code from the beginning, and many are showing great success in college, graduate school, and specifically in the STEM fields. If you think about all of this history and how long it has taken us to get to this point of math literacy, then losing the Nemeth code in the United States could potentially set math education for the blind back 40 years. Yet some are considering abandoning it instead of maintaining it and switching to UEB for math and science. Let's now look at the learning of mathematics and how important it is to all students, not just those going into the STEM fields. Research by Adelman in 1999 and Hill in 2006 showed that the highest level of mathematics achieved in high school was shown to be linked with successful completion of a college degree in any field of study. Bottom line, higher level of high school math equals higher likelihood of completing a college degree. Although this relates to all students, in my opinion, this finding is especially pertinent to blind students. I urge my college-bound students to take a math class their first semester in college, whether they are majoring in a STEM field or not. Otherwise, if they wait until their senior year, they may never graduate. Quote, "Use it or lose it," unquote, is a very apt phrase. Now, let's think about how brain research and unnecessary cognitive load relates to the learning of mathematics. Working memory within UEB is frequently exceeded. It is acknowledged to hold 7 plus or minus 2 items or bits of information at a time, according to research by Caylett in 2005. Working memory can only hold this information for about 15 to 20 seconds, according to research by McGee and Wilson in 1984. Because UEB passages are longer, in math the student will have difficulty keeping what they are reading in working memory. Automaticity, the ability to perform a skill automatically or unconsciously, is affected because the same cell in UEB has an entirely different meaning in Nemeth. Fluency in reading is affected by automaticity. If reading more symbols is required to distinguish numbers from letters, fluency can suffer. Here is a quote from a blind college STEM student on cognitive load. Quote, "Think of the cognitive load. I must physically touch each one of those characters, keeping in mind how the placement of one might affect the meaning of another. Meanwhile, the problem must be held in my very limited short-term memory space," unquote. That was from Amanda Lacey, computer science major, University of Texas at Austin. How many modes and indicators are too many? Any comparison of UEB math and Nemeth code must include a discussion of upper cell numbers. The fundamental shortcoming in the development of UEB for math and scientific notation is the use of upper cell numbers, which creates conflict with many other symbols in both literary and mathematical notation. Use of numbers in the upper part of the Braille cell greatly adds to the length of mathematical expressions, especially in algebra, linear algebra, and calculus, where alphabet number combinations are frequent. 20 to 35% more characters than Nemeth code. This information is gleaned from the research by Knowlton and Wetzel in 2006. If you are a Braille reader, please look at your accompanying Braille document entitled Example Slides in Braille and find Example 1. Otherwise, look at Example 1 on the PowerPoint done in SimBraille for easier visual readability. You may access all 10 examples in a similar fashion. And now for Example 1, which illustrates the problem with using upper cell numbers. We have the equation 3a plus 4x equals 10 written in print, UEB, and Nemeth. The numbers 3 and 4 are coefficients, and the a and x are variables, each representing a number. The UEB version takes up 16 cells of Braille, and the Nemeth version takes up 13 cells of Braille. The UEB version begins with a numeric indicator so that the reader knows that the next cell is a number 3. Otherwise, it would look like a C. The third cell contains a grade 1 symbol indicator to let you know that the next cell is a letter A. Otherwise, the reader might think it was a number 1, since in UEB the letters A through J also represent the numbers 1 through 9 and 0. The next two cells are the UEB addition symbol. The seventh cell has another numeric indicator to let the reader know that the eighth cell is a number 4. Otherwise, it would look like a D. There is no need for a grade 1 symbol indicator in the ninth cell because the variable X will not be confused with a number. X is not one of the letters A through J that also represent numbers. Then we have the required space before we have the 2-cell UEB equal sign, followed by another required space. The last 3 cells are the numeric indicator, followed by a 1 and a 0. The reader knows that these are numbers and not the letters A and J because of the numeric indicator. The Nemeth version begins with a numeric indicator, so the reader knows that they are now in math. This is followed by a number 3, followed by a letter A, followed by a 1-cell addition symbol, followed by a 4, followed by an X. Then we have the required 2-cell Nemeth equal sign, followed by another required space. The last 3 cells are the numeric indicator, followed by a 1 and a 0. The numeric indicator must be used at the beginning of a Braille line or after a space. There is no confusion as to what is a number or what is a letter representing a variable. They are different symbols. The letters A through J are all in the upper part of the cell, and the numbers 1 through 9 and 0 are all in the lower part of the cell. The addition operation symbol only takes 1 cell in Nemeth, whereas the UEB symbol takes 2 cells. If a student constantly has to think about whether the same symbol is a letter or a number, it will slow down their fluency. We were just reading this simple equation. Imagine trying to write this equation and having to constantly determine whether you need to write a grade 1 indicator or not, based on whether your variable is a letter from A to J or not. This has nothing to do with the mathematics involved. By the time a Braille student has figured out how to write the equation in UEB, the rest of the class is on to the next equation. Hopefully, you are beginning to understand why STEM people favor lower cell numbers. The following quote is from Cary Sapalo's bullet points in his address to BANA in 2012. Cary is currently a research scientist in the Department of Chemistry at Purdue University. He is also the president and founder of the company Independent Science. Furthermore, he is the chair of the BANA Ad Hoc Committee on Chemistry. Cary said, quote, Nemeth code's use of lower cell numbers allows the upper part of the Braille cell to be used for mathematical functions critical to the overall successful use of the code for mathematics, unquote. UEB's use of upper cell numbers introduces ambiguity by using the same symbols for numbers and letters. This creates a need for a second symbol to distinguish between them. If you are a Braille reader, please look at your accompanying Braille document entitled Example Slides in Braille and find Example 2. Example 2 illustrates the advantage of using lower cell numbers. We wanted to illustrate inverse and composite functions, so we have the equation, the inverse of f of x equals g of h of x, written in print, UEB, and Nemeth. The UEB version takes up 33 cells of Braille, and the Nemeth version takes up 19 cells of Braille. The UEB version begins with a grade 1 passage indicator, which uses 3 cells, dots 5, 6, used 3 times. According to the UEB technical manual, quote, more complex algebraic equations are best enclosed in grade 1 passage indicators. This will ensure that isolated letters and indicators, such as superscripts, are well defined without the need for grade 1 symbol indicators, unquote. Although the terminology of grade 1 symbol indicator has a mathematical connotation, the terminology of grade 1 passage indicator does not. We don't have passages in mathematical expressions. This is an indication that UEB was written for a literary context, not a technical one. The 4th cell contains F. The 5th cell contains the symbol announcing an upcoming superscript. The 6th through 11th cells are needed to write the -1 superscript. The 6th and 11th cells are opening and closing grouping symbols, which are not in print. I refer to these as ghost parentheses. The 7th and 8th cells are needed for the 2-cell negative symbol. The 9th and 10th cells are needed for the 2-cell number 1. Otherwise, the reader would read it as an A. The 12th and 13th cells are the opening parenthesis, followed by the X, followed by the 15th and 16th cells as the closing parenthesis. Then we have a required space, the 2-cell equal sign, and the required space. The remaining cells are relatively straightforward with just letters and 2-cell opening and closing parentheses. However, you need 2 cells at the end for the grade 1 passage terminator. That's dots 5, 6 followed by dot 3. Notice the cognitive load on each side of the equation. Remember that working memory can hold 7 plus or minus 2 bits of information. That means between 5 and 9, but the left side of the equation is 16 cells long, and the right side of the equation is 13 cells long. Both of these easily surpass the maximum of 9 bits of information. The Nemeth version begins in the first cell with F, followed by the upcoming superscript indicator, followed by the negative symbol, followed by 1. You do need a return to baseline indicator, dot 5, and then we have a 1-cell open parenthesis, X, 1-cell close parenthesis, and you have completed the left side of the equation. Oh, I wish we had a return to baseline indicator in print. Then you have your required space, 2-cell equal sign, followed by a space. On the right side of the equation, it is very straightforward with just letters and 1-cell opening and closing parentheses. Notice that in Nemeth, both sides of the equation were less than 9 cells long. Here are a few concerns from a blind computer programmer. English itself is far from unified. Despite significant differences in Braille codes, in spelling of words, and differing punctuation standards, readability has never been of any significant difficulty, with the exception of math and science. We have blind children in the United States excelling in science and mathematics today, due in significant part to the Nemeth Code. Given these issues, his concern is whether or not it is reasonable to suggest that countries whose primary reading experience has been the British Braille and Maths Code dictate to the United States what we read, despite our 3 generations of experience with Nemeth Code. We have the most Braille material, the most Braille readers, and the most sophisticated series of Braille codes anywhere in the world. Teaching UEB math in some states, or for some students, and Nemeth Code for others, is at best impractical and probably impossible. The two systems come from very different places and represent completely antithetical approaches to the presentation of math and science materials. It is not practical to jettison over 40 years of Braille transcription, teacher training, and student learning in pursuit of an ideal whose existence is questionable. It is a price that no other UEB-using country has been asked to pay. No validation exists that transitioning to UEB math would have any positive effect for the United States. Finally, no conversation about UEB math can be held without the acknowledgement of the deeply flawed premise on which this code is based, the use of upper numbers and the consequent requirements of myriad indicators and Braille-related modifiers. To date, UEB has received the most adverse attention due to its inability to adequately or appropriately represent math and science notation. An equally problematic area for UEB is computer Braille. As lacking as it is for mathematics and science notation, UEB's inherent structural deficiencies are amplified even more when it comes to computer reading, and even more so with computer writing. Chris Gray has written extensively in the past about the need for a one-to-one representation between a Braille and print character in computer notation. The need is no less important today than in the past. The Computer Braille Code, CBC, was designed to maximize this one-to-one relationship. The abandonment of CBC for UEB's computer notation might possibly set computer Braille back almost 30 years. How does this relate to math and science, you ask? According to Chris Gray from the Alliance for Braille Literacy, if UEB computer notation is to survive as a viable standard, how is reading and writing really going to work with a Braille display? To write the number 1 on a Braille keyboard, the user will have to enter first the numeric indicator and then the letter A. But if the QWERTY computer keyboard is used, a single number 1 is pressed. Will the Braille display then show 2 symbols for the UEB representation? To learn more about what Chris is doing, please visit www.all4braille.com. Here are some thoughts from a senior software developer. The use of UEB math will impede online delivery of accessible math to visually impaired students. The use of UEB math will increase the cost of supporting software. Removal of as many indicators from the code as possible is the recommendation. Each additional indicator in the code and each overloaded symbol in the code increases the cost and complexity of the software needed to support it. UEB Math upper cell numerals introduce at least 10 new symbol conflicts, 1 and A through 9 and I, and then 0 and J. These conflicts are commonplace and cannot easily be resolved in software for processing mathematical content. The Nemeth math encoding can be almost exactly mirrored in a software program to capture structured math markup. The UEB math encoding cannot. It is already difficult to make math accessible to people who are blind, but it is even more difficult when the Braille is complicated with additional indicators occupying even more space. In software, flexibility increases cost, so you have to justify what you get in return. So are you going to justify UEB math by making it too complicated for any software producer to support it? Continuing along these lines, how do we get from flexibility to complexity? An authoring tool for math, such as an equation editor, must establish conventional behavior for each math operator it supports. These conventional behaviors include things like how to type expressions that use the operator, how to navigate between arguments associated with the operator, how to encode the operation in a markup language such as Presentation MathML or Nemeth Braille, and so on. It is convenient to express these behaviors as transformation rules, and if each operator has its own set of rules, and if there are only a small number of such rules for each operator, the number of rules is proportional to the number of operators. If the rules for an operator depend on other operators, then the number of rules may be proportional to the square or even the cube of the number of operators. For example, 100 rules for 100 operators is reasonable. 10,000 rules or 1 million rules for 100 operators is not. When rules become dependent on the behavior of other rules, then we add exponential complexity. If you are a Braille reader, please look at your accompanying Braille document entitled Example Slides in Braille and find Example 3. Example 3, how flexibility gets us to complexity. We have the equation 3x minus 4y plus y squared equals x squared written in print, UEB, and Nemeth. The UEB version takes up 27 cells of Braille, and the Nemeth version takes up 17 cells of Braille. The UEB version begins with a grade 1 passage indicator in the first 3 cells. The 4th cell contains the numeric indicator, so that we know the 5th cell is a 3 and not a C. Then we have the variable x followed by the 2-cell minus symbol. The 9th cell contains the numeric indicator, so that we know the 10th cell is a 4 and not a D. Then we have the variable y followed by the 2-cell plus symbol and another y. The 15th cell lets us know that the y has a superscript, and the 16th cell containing a numeric indicator tells us that the next cell is a 2 and not a B. A space follows, so we know we are now back to baseline. After the space, we have the 2-cell equal sign followed by another required space. In the 22nd cell, we have an X followed by the superscript indicator followed by the numeric indicator telling us that the next cell is the number 2 and not the letter B. Cells 26 and 27 are the grade 1 passage terminator. The Nemeth version begins in the first cell with a numeric indicator followed by 3x minus 4y plus y, upcoming superscript 2 on the left side of the equation. Then we have the required space, 2-cell equal sign, followed by the required space. On the right side of the equation, we have x, upcoming superscript 2, and we are done. Note that this particular equation could also be written in UEB without the grade 1 passage indicator and terminator, because the left-hand side of the equation is in grade 1 mode, following the numeric indicator. On the right side of the equation, you would need the grade 1 symbol indicator after the X to alert us that the next cells represent a superscripted 2 and not a B, and we are done. This version takes 23 Braille cells. Although a student could probably read either version, imagine the time it will take to decide which way he or she should write the equation. This same software developer was very impressed with Nemeth Braille, stating that, quote, "It was way ahead of its time," unquote. He then wrote the following timeline to explain his reasoning. Tech Math Typesetting, 1978. Mathematica Computer Algebra, 1988. W3C Content MathML, 1997. Unicode Math Symbols, 2002. Stix Math Fonts, 2008. Nemeth Braille Math Encoding, 1946? Dr. Abraham Nemeth initially developed the Nemeth code for himself. As a professor of mathematics who just happened to be blind, Dr. Nemeth was able to write print mathematics on the blackboard for his sighted students. However, he wanted to be able to take mathematical notes that he could read himself. The Taylor Code was used for writing mathematics in Braille at that time, and Dr. Nemeth felt that it was terribly cumbersome. So he took it upon himself to write his own, much more efficient code, and he was nice enough to share it with the rest of us. In case you need a little more detail on our software developer's timeline, the Nemeth Braille encoding system provides a more stable and reliable encoding for mathematical notation than Donald Knuth's Tech Math typesetting system, widely regarded as one of the most stable tools in all of scientific computing. The Nemeth Braille encoding system provides a more extensive system for capturing the notation for a mathematical expression and a more precise system for capturing the structure of a mathematical expression than the World Wide Web Consortium's W3C's Content and Presentation Markup Language. The Nemeth Braille encoding system includes math symbols that are not included in the Unicode standard for character encoding. The Nemeth Braille encoding system includes math symbols that are not included in the Stix math fonts. The Nemeth Braille encoding system includes techniques to address issues in mathematical usage that are still problematic in other languages, such as recursive structures, constructed symbols, unit abbreviations, and textual content. The Nemeth Braille encoding system was designed in a way that enables efficient processing and translation by computer software. These thoughts come to us from Sam Dooley, Manager, Software Development, Pearson, who first began learning the Nemeth Code in February 2015 and already understands it very well. What does that say about the intuitive nature of the Nemeth Code? Next, we will look at issues identified by Carlton Walker, parent, attorney, and teacher of blind students. Currently, all math and science materials are in Nemeth Code. Adding UEB math will be duplicative and expensive. Having two codes will mean that all materials will need to be produced and available in each code. This could lead to shortages in materials. Adding UEB math will erect barriers to relocation within the United States. Families needing to move for employment or security reasons risk putting their children behind in math due to the need to learn a new Braille math code. They may well fall months behind in math classes due to a lack of familiarity with the new code. This will be particularly difficult for children of military families who will almost certainly move several times throughout their school careers. This could also be particularly difficult for children from families of lower socioeconomic means due to a need to relocate more often. There is no reason to set up a system that will automatically place Braille readers at an academic disadvantage upon relocation. Due to the need to teach a new math code to move-ins, teachers of the visually impaired will have less time to instruct children. TVIs are in short supply as it is. We should not be creating another unnecessary drain upon their time. Adding UEB math will create a problem with accessible math textbooks. All current math textbooks have been produced in Nemeth Code. It will be time-consuming and expensive to recreate this work in UEB math. Students will likely go without math textbooks during this transition period. The duplicative nature of maintaining two math codes in the United States introduces an unnecessary expense and will further delay the timely access to accessible math materials for students who are Braille readers. Unlike Nemeth Code, which has a separate certification for transcribers who are producing technical notation, there is no certification for UEB math transcription in the United States. If UEB math is adopted by some states, then uncertified transcribers will be doing the transcription because there is no certification for UEB math transcription. This situation puts students at high risk of receiving poor quality math transcription. All students with an IEP are guaranteed a free, appropriate public education, FAPE. Poor quality textbooks violate FAPE and place school districts at risk for litigation based upon the poor quality of textbooks Braille readers receive. On July 9, 2015, NFB passed Resolution 2015-29. The complete resolution is available at https://nfb.org/2015 resolutions. The last 2 points related to Nemeth Code are paraphrased as follows. NFB calls upon state departments of education to eliminate needless confusion and unnecessary cost by using the Nemeth Code for mathematics and science notation, with BANA's guidance for Nemeth in UEB contexts as the standard for Math Braille. NFB urges BANA quickly to clarify that although timelines and processes for UEB implementation are set at the state level, Braille code standards are not set by individual states, and to indicate unequivocally that the Nemeth Code with the guidance for Nemeth in UEB contexts is the standard for mathematics Braille in the United States. Mark A. Riccobono, president of the National Federation of the Blind, followed this up with a letter to the state departments of education on August 24, 2015. And now we would like to quote from some published research. From Wetzel and Knowlton, JVIB, April through May 2006. Quote, the participants clearly stated that any changes to the code that would make Braille more difficult to read would not be in the best interest of the current population, many of whom could be greatly hampered by learning a code that these professionals considered to be more complex, unquote. Quote, the UEB study lacked input from professional Braille users in the fields of mathematics and computer science, unquote. More from Wetzel and Knowlton. Quote, there is a significant question remaining as to the impact of eliminating multiple contractions in a passage. It is a question that should be addressed before global changes to the Braille code are made. These issues can be most effectively addressed by conducting further research, unquote. Quote, perhaps some of the most significant research on any Braille code needs to address a vast array of cognitive issues that are related to learning and using Braille as a reading and writing system, unquote. Even more from Wetzel and Knowlton. Quote, the field would benefit from studies that address limits to short-term memory, that's working memory, as they apply to the reading, recall, and writing of Braille, unquote. Quote, writing Braille is an area of research that is yet to be addressed, unquote. Quote, when one looks at the results collectively, it is clear that much more research is necessary before professionals will have sufficient knowledge to make wise decisions regarding changes to the Braille codes, unquote. Furthermore, from Wetzel and Knowlton, quote, to date, no studies have addressed the transcription and comprehension of graphic material in Braille. A unified code needs to address this kind of information in addition to pure literary text, unquote. UEB would be more expensive to produce than EBAE or Nemeth Code due to longer passages. Arithmetic computation, quote, required 17% more characters and algebra required 20 to 35% more characters, unquote. This would mean more expense to produce the books. Arithmetic and algebra books are the longest ones. There is one other piece of research from Holbrook and McCuspy, JVIB, September 2010. It was a study of UEB technical material involving 5 adult participants. As stated in the article, quote, the participants were required to be Braille readers who were employed in highly technical fields, had limited previous knowledge of the UEB code, and did not have a strong opinion, pro or con, about the UEB code. Thus, we had a limited pool of individuals from whom to draw, unquote. In other words, anyone who had a strong opinion about Nemeth was rejected, and few people met the criteria. 5 participants were found for the study. 2 of those participants didn't even currently use Nemeth code. More on the Holbrook and McCuskey research. The study did not look at the codes from the perspective of whether UEB would meet the same needs as the current Nemeth code. It was only done over 2 days. Participants were asked about transition for adults who use Braille, not for students learning math and using UEB. Participants did talk about their concern for transition because of the UEB using symbols from previous codes in entirely different ways. And participants mentioned back translation as a strength of UEB, but efficient back translation has not been fully verified within the field of blindness technologies. Based on this research, several STEM blindness professionals are in agreement with Pogren and Wibbenmeyer's suggestion from 2008 that we should consider the development of better and more uniform TVI personnel preparation programs and higher state certification requirements. And we should conduct research comparing Nemeth and UEB. What is the relationship between success in math and science courses and the Braille code students use? Although we have already looked at a comparison of 3 secondary math examples, I found that most people want to know what's happening at the elementary level. Some people are recommending that we start with UEB math and the lower grades and just switch over to Nemeth code when the student begins higher mathematics. Let's see what you think as we do a Braille code comparison of just the basics. Here are some math and science samples of UEB and Nemeth. I took the UEB samples straight from the UEB guidelines for technical material 2008 version, updated August 2014, and added the Nemeth counterpart. If you are a Braille reader, please look at your accompanying Braille document entitled Example Slides in Braille and find Example 4. We will be using it extensively for the next several slides, so keep it handy. And now for Example 4, which is an example of spatial addition. You have the addition problem of 456 plus 34 equals 490, written spatially in print, UEB, and Nemeth. You will note that there are 2 versions of UEB. The first version of UEB shows numeric indicators being used for each number with the 2-cell plus sign placed at the left as in print. The second version of UEB uses the numeric passage indicator to begin the problem, dots 3456, dots 3456, and the numeric passage terminator at the end of the problem, dots 3456, dot 3, which set the numeric mode and grade 1 mode for the enclosed text. In a numeric passage, numeric indicators are not used. The placement of the operation sign does not need to follow print, but can be adjusted to suit local teaching practices. Indentation has been used to keep the columns of the calculation clear of numeric indicators. Which version will the TVI choose to teach his or her elementary student? Which version will the textbook transcriber choose? Which way will the standardized testing entity choose? Will this young elementary student need to learn at least 2 or possibly 3 different versions of every possible problem? In Nemeth code, the numeric indicators are not used, all numbers are lined up in columns, and the plus sign is placed at least 1 column of cells to the left of the widest column of numeric symbols which appear in the part of the arrangement above the separation line. The separation line must be made 1 cell longer at either end than the overall width of the rest of the arrangement. This will be done in exactly the same way in the school setting, in the textbook, and on standardized tests. Now for example 5, which illustrates linear addition. You have the addition problem of 3 plus 5 equals 8, written linearly in print, UEB, and Nemeth. You will note that there are 2 versions of UEB. The first version of UEB takes up 14 Braille cells. we have the numeric indicator 3, space, plus, space, numeric indicator 5, space, equals, space, numeric indicator 8. The UEB Technical Manual suggests, quote, when presenting Braille mathematics to younger children, include spaces before and after operation signs and before and after comparison signs, unquote. The second version of UEB takes up 12 Braille cells. We have the numeric indicator 3 plus numeric indicator 5, space, equals, space, numeric indicator 8. The UEB Technical Manual suggests, quote, for older students who are tackling longer algebraic expressions, there needs to be a balance between clarity and compactness. A good approach is to have the operation signs unspaced on both sides, but still include a space before and after comparison signs, end quote. Which version will the TVI choose to teach his or her elementary student? Which version will the textbook transcriber choose? Which way will the standardized testing entity choose? Will this young elementary student need to learn at least 2 or possibly 3 different versions of every possible problem? The Nemeth version takes up 10 Braille cells. We have the numeric indicator 3 plus 5, space, equals, space, numeric indicator 8. There is one Nemeth version for students of all ages. There is no space before or after operation signs, and there is always a space before and after comparison signs. In this case, the equal sign. Now for example 6, a simple chemical formula everyone knows. H2O is written in print, UEB, and Nemeth. The UEB version takes up 8 cells. We have capitalization indicator H, grade 1 symbol indicator, subscript indicator, numeric indicator 2, capitalization indicator O. The Nemeth version takes up 5 cells. We have capitalization indicator H, 2, capitalization indicator O. Next is example 7, a simple numeric fraction. The fraction 5/8 is written in print, UEB, and Nemeth. The UEB version takes up 4 cells. We have the numeric indicator 5/8. Wow! Fractions are going to be easier than Nemeth, you say. The Nemeth version takes up 5 cells. We have the open fraction indicator 5/8, closed fraction indicator. But wait a minute. What's a simple numeric fraction? I've never used that terminology in my math classroom. All the elementary teachers just call them fractions, and so do I. Reading the UEB Technical Manual was the first time I'd ever heard this terminology, and here is what they say. Quote, a simple numeric fraction is one whose numerator and denominator contain only digits, decimal points, commas, or separator spaces, and whose fraction line in print is drawn between the 2 vertically or nearly vertically arranged numbers, unquote. So that leads us to example 8 and how to Braille a general fraction. This is another new terminology that will never be used in the general education classroom since it was defined by the UEB Technical Manual. Quote, if the numerator or denominator is not entirely numeric, as defined in section 6.1, then the general fraction indicator should be used, unquote. The fraction x/2 is written in print, UEB, and Nemeth. The UEB version takes up 9 cells. We begin with the grade 1 word indicator .56 used twice. Then the open general fraction indicator X, the 2-cell general fraction line symbol, the numeric indicator 2, closed general fraction indicator. So, inserting one variable in place of a number changes the entire way one brailles a fraction in UEB. From a mathematical viewpoint, X represents a number, so mathematically speaking, this is totally illogical. This thwarts the math teacher's efforts considerably if a student is made to think in this manner. Also, when listening to the general education teacher in class, a Braille reader will need to listen to the entire fraction before beginning to write the fraction because he or she first has to determine whether it is a simple numeric or general fraction. By the time the student has determined this, the class is off to the next fraction. In a recent webinar on September 3, 2015, entitled Technical Materials, UEB and Nemeth, presented by Frances Mary DeAndrea, the same example was brailled slightly differently. The webinar example began with a grade 1 symbol indicator instead of the grade 1 word indicator. Since my example came directly from the UEB manual, it would seem that the manual is open to a different interpretation. And if that is the case, then it could cause problems with accurate transcription. The Nemeth version takes up 5 cells, and the brailing technique is exactly the same because, unlike UEB, there is no mathematical differentiation between fractions based upon whether or not a variable is used. We begin with the open fraction indicator, X, 1 cell fraction line indicator, 2 closed fraction indicator. Now we are ready for example 9, which deals with superscripts. We have 3 separate sample items to illustrate when UEB braille grouping symbols are required. The first sample is X squared, written in print, UEB, and Nemeth. The UEB version takes 5 cells. We have X, grade 1 symbol indicator, which by the way is a subscript indicator in Nemeth. Superscript indicator, numeric indicator, 2. The Nemeth version takes 3 cells. We have X, superscript indicator, 2. The second example is X squared times Y, written in print, UEB, and Nemeth. The UEB version takes 6 cells. We have X, grade 1 symbol indicator, which remember is a subscript indicator in Nemeth. Superscript indicator, numeric indicator, 2, Y. The superscript indicator only applies to the next individual symbol, in this case the 2 and not the Y, so there is no clearly defined end to the exponent. The Nemeth version takes 5 cells. We have X, superscript 2, return to baseline, Y. The third example is X to the 2Y power, written in print, UEB, and Nemeth. The UEB version takes 9 cells. We thought we were getting the hang of this, but now we have a new rule. This expression requires braille grouping symbols. So we start with the grade 1 word indicator, that's dots 5, 6 twice, followed by X, superscript indicator, open braille grouping symbol, numeric indicator 2, Y, closed braille grouping symbol. Once again, there is not a clear definition of what constitutes a word or a passage in math notation, but these indicators are often used in UEB math. As the UEB technical manual states, quote, refer to the definition of an item in section 7.1 to decide when braille grouping symbols are required. Note that the braille grouping symbols themselves have an alternative grade 2 meaning, unquote. Personally, I think that's very confusing. The Nemeth version takes 4 cells. We have X, superscript 2, Y. The Y remains in the superscript because no return to baseline indicator was used. The space following the expression terminates the superscript. The addition of these UEB braille grouping symbols, what I call ghost parentheses, is superfluous. They are only going to cause confusion in the general education classroom where the print has no such symbols. The Nemeth code deals with this quite easily in a concise, logical fashion. Again, a braille reader listening to this in the classroom will have to wait until the entire expression is read before determining how to even begin to write it. The research touched on the fact that no research was done as to how the adoption of UEB will affect tactile graphics. Although it probably shouldn't even be considered a tactile graphic, I did want to show you example 10, the number line graph x equals 1, created in print, UEB, and Nemeth. The UEB number line graph is 31 cells wide. The left arrow consists of 2 cells, that's dots 1, 2, 5, 6, and dots 2, 4, 6. The right arrow consists of 2 cells, dots 1256, and dots 135. The tick marks are dots 2456. The scale numbers take up twice as much space as those in Nemeth because of all the extra required indicators and the two-cell negative sign. Therefore, the space between tick marks must be elongated to accommodate these numbers. We have the graphed point at 1 indicated with a full cell above the graph. In section 4.4.2, the UEB Technical Manual tells us that we can make code accommodations when space is at a premium as long as you include a transcriber's note. So we will have lots of different versions of this type of graphic. Another example of flexibility leading to complexity. The Nemeth number line graph is 19 cells wide. The left arrow consists of dots 246 and looks like a print left arrow. The right arrow consists of dots 135 and looks like a print right arrow. The tick marks are dots 1, 2, 3, 5. The non-use of numeric indicators and the one cell negative sign keeps the graph compact. The only thing that is the same is the graphed point at 1 indicated with a full cell above the graph. Students have been independently creating number line graphs in this Nemeth manner for years. It is also documented this way in the BANA Tactile Graphics Guidelines. This has been the recommended method for all textbooks and standardized tests in the United States. So, how do Nemeth and UEB Math compare regarding codebooks and guidelines resources? Nemeth has the Nemeth Braille Code for Mathematics and Science Notation, 1972 revision, 255 pages. UEB Math has the UEB Guidelines for Technical Material, 2008 version, updated August 2014, 87 pages. Nemeth has the Braille Code for Chemical Notation, 1997, 147 pages. UEB Math has Section 16, Chemistry, within the UEB Guidelines for Technical Material, 2008 version, updated August 2014, 9 pages. Let's look at some more codebooks and guidelines. Nemeth has Graphing Calculator Guidelines, March 2015, Proposed Guidelines, 58 pages. UEB Math has Section 3.5, Calculator Keys, within UEB Guidelines for Technical Material, 2008 version, updated August 2014, 1/3 of a page. Nemeth and UEB Math both have Braille Formats, Principles of Print-to-Braille Transcription, 2011, currently being revised to align with UEB, 675 pages. Continuing on with codebooks and guidelines, Nemeth has the Guidelines and Standards for Tactile Graphics, 2010, 362 pages, and the Guidelines and Standards for Tactile Graphics, 2010 Supplement, examples 1 through 35, and I'm sorry I didn't count the pages on that. UEB Math has Section 4.4 Diagrams within the UEB Guidelines for Technical Material, 2008 version, updated August 2014, 3 pages. ICEB Resolution 6, May 2012, recommended the BANA Guidelines and Standards for Tactile Graphics and Supplement, currently being revised to incorporate UEB, be considered. And you can find that information at www.iceb.org/GARES12.htm. Not even counting the Braille Formats and Tactile Graphics Guidelines and Supplement, the Nemeth Code has 460 pages of BANA code books and guidelines, whereas UEB Math has only 87 pages of ICEB guidelines. Obviously, much detail is left out in UEB Math, and because of this lack of specificity, much is left up to the transcriber, which could cause inconsistency in transcribed materials. Transcribers do not like flexibility. They prefer rules and lots of examples. Nemeth within UEB context. According to Jennifer Dunham, representative of the NFB to the BANA Board and BANA Board Chair, to ensure that the Nemeth Code can continue to be used as UEB is implemented, a method has been developed to switch between Nemeth Code for the mathematical expressions and UEB for the text around the mathematics. This is similar to our current use of switching to computer braille code for email addresses and the like. The symbols used to show the switch between the codes are included in the official rules of UEB. Jennifer Dunham goes on to say, guidance on how to use Nemeth Code within UEB entitled Provisional Guidance for Transcription Using the Nemeth Code within UEB Contexts is available at www.brailleauthority.org/math-science.html. BANA continues to refine the guidance based on suggestions from those who use it. You may be wondering why such switching is necessary. An unambiguous switching method eliminates conflicts between codes by making it clear which code is in effect when reading or writing. Also, as the use of electronic means to read and write in both print and braille proliferates, the need for accurate translation both from print to braille and from braille to print becomes an increasingly critical consideration. This switching method makes accurate electronic translation in either direction possible so that mathematics can be communicated between print users and braille users using Nemeth Code within a UEB context. Why we think UEB for math and science is problematic. Upper cell numbers, numerous new indicators, longer expressions, insertion of superfluous braille grouping symbols that do not appear in print, and notice that these last two bullets are bolded because teachers really are concerned about these two items. Use of terminology that is not used by mathematics teachers. Ambiguity of how to write fractions dependent upon the presence of variables. If you want additional information, please feel free to contact me at the Texas School for the Blind and Visually Impaired Outreach Programs, 1100 West 45th Street, Austin, Texas, 78756, USA. My email address is susanosterhaus@tsbvi.edu. That's SUSANOSTERHAUS@tsbvi.edu. Or check out the following resources. My website address is www.tsbvi.edu/math. I have several free online videos on various accessible math tools and technology and the Nemeth Code at www.tsbvi.edu/distance/Osterhaus_math_intro.html. There are even more videos on the Orion TI-84 Plus Talking Graphing Calculator and the Nemeth Code at library.tsbvi.edu/browse/category/9. I'm also a member of 3 BANA committees: the Mathematics Braille Technical Committee, the Tactographics Technical Committee, and the Ad Hoc Committee on Standardized Tests, and our work is published on the BANA website. I would like to give a big thank you to those working behind the scenes providing steadfast support. Dan Brown, Senior Quality Assurance Engineer, Blindness Technologies, School Line of Business, Pearson Assessment Center, for quality control on the accessibility of the PowerPoint and Braille examples. Sarah Larkin, Math and Science Consultant, Iowa Educational Services for the Blind and Visually Impaired, Vinton, Iowa, for assistance with polishing the PowerPoint and script writing. Jan McSorley, Head of Accessibility, School Line of Business, Pearson Assessment Center, for assistance with recording and production. I am now going to scroll through multiple slides of references. But I'm not going to read through all of them because we have posted a document that lists all of them at http://accessibility.pearson.com/Braille 4 math-science. The Braille documents mentioned earlier are also available at this same location. If you would like a PDF version of the entire PowerPoint, you may contact me directly. Thank you so much for your kind attention.